Hello students, so welcome to part 4 of the lecture series on filter design. We have already covered 3 parts of the lecture series and we have discussed 2 methods to convert analog filter into digital filter. So we are on now up to the, now we will start method 3 for filter design. For filter design, that is from analog to digital filter, and this method is called bilinear transformation method. Okay, now as we have seen that the method 1, that was backward difference method, and we have seen the method 2, that is impulse invariance transformation. Now in method 1 we have clarified that it is not suitable for high pass filters and the band reject filters. In impulse invariance transformation, the transformation of the left half plane was into the unit circle in the z plane. So left half of the s plane into the unit circle in the z plane. But there was a problem that if you see the transformation from continuous frequency omega to discrete frequency sigma, then it is many to one transformation, and that's why impulse invariance transformation method is also not suitable for the higher frequencies. That is, it is also not suitable for the high pass filters and the band reject filters. So these two methods are not suitable for the high pass filters and the band reject filters. So we designed a new method that is called bilinear transformation method, BTM, where there is one-to-one mapping between S and Z plane. So there is no problem of many to one mapping. Okay, there is one to one mapping here. So let's see how it is designed. Okay, so let's start with the system, that is analog system HAS, that is equals to B upon S plus A. So we can say that YS is equals to B upon S plus A into XS. YS into S plus A is equals to B times of XS, and A times of YS plus S times of YS is equal to B times of XS. So in the time domain, this can be written as dyt over dt plus A times yt is equal to B times xt. So now if we integrate this equation over the time axis on the limits t equals to n minus 1 capital T to nt, then we can see that the equation will become dyt over dt multiplied by dt integrating from n minus 1 capital T to nt plus A times of n minus 1 capital T to nt yt dt is equal to B times integration n minus 1 capital T to nt xt. Okay, dt. So now we will use a rule that is called trapezoidal rule of integration, which says that integrating n minus 1 capital T to nt AT dt is equal to capital T by 2 value of A at nt minus plus value of A at n minus 1 capital T. So using this trapezoidal rule of integration on the above equation, we can see that. So we'll get from this above equation y of nt minus y of n minus 1 capital T plus a capital T by 2 y of nt plus y of n minus 1 capital T, okay, is equal to bt by 2 x of nt plus x of n minus 1 capital T. Okay. Now if I remove capital T from here, because capital T is a constant, so the above equation can be written as yn minus 1 plus at by 2 yn plus yn minus 1 is equal to bt by 2 xn plus xn minus 1. Now taking the z transform of this equation, we can see that yz 1 minus z inverse at by 2 yz 1 plus z inverse is equal to bt by 2 xz 1 plus z inverse. Now from the above equation, we can see that hz, that is equals to yz upon xz, will be equal to b upon 2 upon capital T 1 minus z inverse upon 1 plus z inverse plus a. Now if we compare the equation, let us say this is equation number 2 and the system which we had written in the starting, that is this is the system number 1. So this is equation number 1 and the equation number 2. Now this is the analog system in equation number 1, and in equation number 2 we have the digital filter. Okay, so now comparing the digital filter and the analog filter in equation number 2 and equation number 1, we can say that S is equal to 2y capital T 1 minus z inverse upon 1 plus z inverse. Okay, so this is the important result for bilinear transformation, the relationship between S and Z. So they can ask you the relationship in 1 mark per question directly also. Okay, now this can be rearranged and S is equal to 2 upon capital T Z minus 1 upon Z plus 1. So this is also a relationship. Okay, and you can rearrange this equation and you will get that Z is equal to 1 plus capital T by 2 S divided by 1 minus capital T by 2 S. Okay, so these three relationships, you must just have a look at these relationships, because they can ask you these questions like in 1 marker question, like what is the relationship between S and Z. Okay, so I have to add a page here. Okay, now so So now let's move on. And okay, now this is the relationship between S and Z. Okay, now as we know that Z is equals to R e to power j, the digital frequency. So now putting this, we get that S is equal to 2 by capital T using this equation, R e to power j, the digital frequency, minus 1 upon R e to power j, digital frequency, plus 1. Okay, now multiplying the numerator with R e to power j sigma plus 1, multiplying in the numerator R e to power minus j sigma plus 1 upon R e to power minus j sigma plus 1. Okay, now solving this, we will get 2 upon capital T. Okay, now we will solve this and we'll get R square plus R e to power j sigma minus R e to power minus j sigma minus 1 divided by R square plus R e to power j sigma plus R e to power minus j sigma plus 1. Okay, now we will solve this. We will get 2 upon capital T. So this will give us a cos term, and this will give us a sine term. So this will give R square plus 1 divided by R square plus 2R cos sigma plus 1 plus j 2R sine sigma divided by R square plus 2R cos sigma plus 1. Okay, so this is the, so I can say that this is equal to S. Now S is equals to sigma plus j omega. So the real part of S, that is equals to sigma, is equal to the real part of the right hand side. So real part of the right hand side. So this, the real part sigma will be equal to 2 upon capital T R square plus 1 upon, okay, and the complex frequency, the continuous frequency omega will be equal to 2R sine sigma divided by R square plus 2R cos of sigma plus 1. Okay, so these two equations are there. This is equation number 1 and this is equation number 2. Okay, so this is the important relationship. I don't think no one will ask you this lengthy, this is R square minus 1, sorry, R square minus 1 here. So no one will ask you this expression written in equation number 1 and equation number 2. I'm just telling you for the sake of completion of the bilinear transformation. Okay, now I will add one more page. Okay, now we can see that equation number 1, we can see that whenever R is less than 1, then the real part of s will be less than 0, and when r is greater than 1, then the real part of s will be greater than 0. So we can say that in z plane, the region inside unit circle is similar to the left half of the s plane. Okay, simple. We can see this now from equation number 1. Now equation number 2. So from here we can see that if we have stable analog filter, then it will transform into stable digital filter. Okay, now from equation number 2, if you look at equation number 2, then equation number 2 is this: omega is equals to 2r sine on r square plus 2r cos. Okay, now let us say that we are talking at the imaginary axis, and since the imaginary axis corresponds to the unit circle, or a circle with unit radius, so imaginary axis corresponds to r equal to 1. Imaginary axis in s plane corresponds to r equal to 1, the unit circle in the z plane. So applying the condition of imaginary axis on the equation number 2, we can say that at imaginary axis omega will be equal to 2 sine sigma upon 1 plus 2 cos sigma plus 1. Okay, so the denominator here will be 1 plus 2 cos sigma plus 1. So this will come out to be 2 sine sigma upon 2 plus 2 cos sigma, that is sine sigma upon 1 plus cos sigma, is the imaginary axis, is the omega. Okay, now this can be easily transformed into omega equals to 2 sine omega by 2 cos omega by 2 divided by 2 cos square omega by, so sorry, sigma. Okay, now this can be solved and we will get that this is equals to, I left 2 by capital T, so there is a modification, 2 by capital T is also there. Okay, I just left that. So this will come out to be 2 by capital T tan of omega by 2. So this is the relationship that you should learn. So the continuous frequency omega is equals to 2 by capital T tan of digital frequency divided by 2, or the digital frequency is equal to 2 times tan inverse omega t by 2. So these two relationships are very important, and remember that this is the relationship only at the imaginary axis. On the other axis, for other uh, axis, there will be a different relationship. Okay, so this is very important. Only this you have to learn. So this you have to learn. Okay, now as we know that omega varies from minus infinity to infinity. Now if I put omega minus infinity to infinity values, then this tan inverse will only give me the values from pi to minus pi. Now this is the plot between the digital frequency and the continuous frequency. So the continuous frequency sorry, is varying from minus infinity to infinity, and we can see that the tan inverse function will vary from minus pi to pi. Okay, and we can see that this is one-to-one relationship. One-to-one relationship. Okay, so the problem which we were facing in the impulse invariance transformation, that there was a many-to-one mapping. Okay, that is removed here. But there is a one more problem which we will face. So that problem is called, okay, so this is clear. So one more problem which we will face is the problem of frequency warping. Okay, what is this? Now, since the relationship between the digital frequency and the continuous frequency is non-linear function, so this is why frequency warping is happening. So now let's look at the meaning of frequency warping. So for this, let me copy the figure and paste it here. Okay. Now just look at the continuous frequency omega axis. So let us take these values. So I'm marking the values with green. So these values will be, so these values on the digital frequency axis will be visible over this region. Now for these frequencies, if the width of red and green is same, but you can see that the width of red will be reduced on the digital frequency axis. Similarly, the third one, if I take, then the width will be further reduced on the digital frequency axis. Now what we can see here is that due to the nonlinear relationship, sorry, the relationship was omega t by 2. Okay, so now due to this nonlinear relationship, what is happening is the lower frequencies of the continuous domain, that is omega domain, are expanded on the digital frequency axis, but the higher frequencies of the continuous domain are compressed on the digital frequency axis. So this is what the frequency warping is. Now they can ask you this what is frequency warping in the bilinear transformation. So this is the simple thing, and you can easily visualize this also. The lower frequencies are approximately of the same width on the digital frequency axis, but the red one is reduced and the purple one set is further reduced on the digital frequency axis. So the higher frequencies are compressed on the digital frequency axis. So this is what the frequency warping is. Now let's look at the effect of frequency warping, that what will happen by the frequency warping. So let us say that HA omega is the function of the continuous time filter or the continuous time system, and mod of HA omega shows the magnitude and angle of HA omega shows the phase. Okay, and here we can see that, so I've drawn the figure here. So here we can see that it's a linear phase system. Okay, so we are talking about the continuous time system. Okay, and here the magnitude plot is like this. So it is non-zero over these frequencies, non-zero over these frequencies, and non-zero over these frequencies, and it's a linear phase curve as we can see here. Now the transformation from the continuous frequency to the discrete frequency is drawn here. It's a nonlinear curve. So the magnitude response in the discrete domain will change. Okay, so we'll be mapping here. So what is the mapping taking place? So these frequency mappings are taking place here. Okay, now if we say that the width of these frequencies on the continuous frequency axis is same, let us say this, but the width on the discrete frequency axis will keep decreasing as the value of continuous frequency omega increases. Okay, so we can see that. So the width decreases. Now this is because of the frequency warping. Okay, very simple to understand. Now same is the effect on the linear phase. So if this is a linear phase, then by mapping we will get the phase of the discrete system as a non-linear. Okay, so this is the effect of frequency warping that will take place. Now let's look at one or two examples. So it is given that, so this is question number 1. So the example is HAS S plus 0.1 divided by S plus 0.1 whole square plus 9. So this is the analog filter. We have to convert this into a digital filter with omega r is equal to pi by 2. Okay, so we can see that analog so a digital filter with sigma r is equal to pi by 2. Now in the analog filter, omega r is equals to 3. Okay, so you can see that. So since we have the relationship that omega is equal to 2 by capital T 10 of okay. So we can get the relationship that 3 is equal to 2 by capital T tan of I by 4. So T is equal to 2 by 3. So we get capital T value. Now, as we know that Hz is equals to HAS, where S is equals to 2 upon capital T 1 minus Z inverse upon 1 plus Z inverse. So easily we can replace S by this function in the equation. So S plus 0.1 upon S plus 0.1 whole square plus 9. 2 by capital T. Now we know 2 by capital T is 2 by 3 Z inverse upon 1 plus Z inverse. So this will come out to be S equals to 3 1 minus Z inverse upon 1 plus Z inverse. Okay. So putting the value of this S, we will get that it is Hz is 3.1 plus 0.2 Z inverse 2.9 Z to power minus 2 divided by 18.61 plus 0.02 Z inverse plus 17.41 Z to power minus 2. So such type of questions can be asked. So similar examples are given. So there is one more example. Let me solve this. Example number 2. So here HAS is given to us, that is 4 upon S plus 3 into S plus 4. Capital T is given to us 0.5. We have to find Hz. So very simple question. So here Hz will be equal to 4 upon S plus 3 S plus 4, and S will be equals to 2 upon 0.5 1 minus Z inverse upon 1 plus Z inverse. Okay, now simply we will put S is equal to 4 1 minus Z inverse upon 1 plus Z inverse, and after solving this we will get Hz will come out to be 1 upon 2 1 minus 1 plus Z inverse whole square divided by 7 minus Z inverse. So these kind of questions can be asked. So this is sufficient for the IIR filter design. In the next part of the lecture, we will be completing the FIR filter design. Hello friends. So welcome to part 5 of the lecture series on the filter design. We have already completed IIR filter design, and we have already talked about some differences of IIR and FIR filters. Now we will start in this section on this part with the FIR filters. So what is the meaning of FIR? The meaning is finite impulse response. So if we have any system which is a digital system or a discrete system having impulse response Hn, and if Hn is non-zero for finite values of n only, then it is FIR filter. Okay. Now as we have seen that in the first part itself, I have taught you that whenever you will find the Z transform of this FIR filter, then HZ will have pole only at z equals to 0 or z equal to infinity. That is, no pole is between z equals to 0 and z equal to infinity. And we also know that ROC is entire z plane except z equals to 0 or infinity or both or none also, because if delta n hn is equals to delta n, then in that case ROC is entire z plane. Okay, 0 and infinity are also included. So except z equals to 0, z equals to infinity or both or none. Okay, now we have seen this thing, and I'm repeating it again because it's a very important property, that when Hn is FIR, then Hz, that is its Z transform or the transfer function of the system, will have poles only at z equals to 0 or z equals to infinity. There is no pole between z equals to 0 and infinity, and ROC is entire z plane except 0 or infinity or both or none. Okay. So now let's look at few properties, because these kind of properties which I'm going to tell you here can be asked in a single marker question in GATE exam or any other competitive exams for electronics student. So the properties, now as we know, the stability of the system means summation of mod of Hn minus infinity to infinity should be less than infinity, and since for FIR filter Hn is non-zero only for few values of n, so FIR filters are always stable as they satisfy the condition given in equation number 1. Okay, because Hn is non-zero only for few values of n, and always it is a finite value, so the sum will also be a finite value. Okay. Second, as we know that IIR filter can never be a linear phase, so the property of FIR filter is that FIR filter can be designed with a linear phase. Okay. Next property. Now this is a very important property. Now let's look at this property. This is a very important property. Now as we know that IIR filter has a pole, always has a pole. So Hz of IIR filter, so let us take Hz of IIR filter as HIIR Z. Let us take a simple example, A upon 1 minus B Z inverse, a simple example. So we will say YZ upon XZ is equals to A upon 1 minus B Z inverse. So by taking, we can say that A times of XZ is equal to YZ minus B Z inverse YZ is equal to AZ. Now converting this into a time domain equation, we will get that Yn minus B Yn minus 1 is equal to A times Xn. This implies yn is equal to a times xn plus b times yn minus 1. So a very important conclusion is that the present value of output in IIR filter, the present value of output depend on, we can see that it is depending on the past value of output. Okay, and here we can see that it is depending on the present value of input also, and there can be other past value of input and other past value of output also, because I have taken a simple system, so that's why only these two terms are coming. So if I write a normal or a general form, then it will be a times of xn plus a1 times of xn minus 1 plus a2 times of xn minus 2 and so on, plus b times of yn minus 1 plus b1 times of yn minus 2 and so on. So present value of output in IIR filter. So write this is a very important property of IIR filter. So for IIR filter, present output will be equal to, or I can say that present output depends on present and past input and also past outputs. And we know that you have seen in the system design, so you have already studied the block representation in the signals and system, block representation of the system in signals and systems, and in controls also. So this is actually representing the feedback, and this is representing the feed forward. So I think you have studied that. If you have not, then please comment here and I will be preparing a video on that also. That's a very simple topic of signals and systems. So this is feedback and this is feed forward. Okay, so since the present output is depending on the past outputs, so this is called a system which has having feedback, and this is called a recursive system. So IIR filters are always recursive system because there always be a pole, and pole always shows a feedback path. Okay, so this thing, I hope that you have already studied the filter, the system design, and that's why I'm not explaining the things here. I will be making a video on that also. So this is a recursive system. So IIR filters are always recursive system, but the FIR filters, since there are no poles here, in FIR filter there is no pole, there is a pole are at only 0 and infinity. So HZ will be of the format A times A plus A1 Z inverse plus A2 Z to the minus 2, A3 Z to the minus 3, that's all, something like that. So if I write YZ upon XZ is equal to A plus A1 Z inverse plus A2 Z to the minus 2, A3 Z to the minus 3, so I can write Yn is equal to A times Xn, A1 times Xn minus 1, A2 times Xn minus 2, A3 times Xn minus 3. So I can see that the present output is depending only on the present input and the past inputs only, and such kind of system where there is no feedback path. So there is no feedback path here. So such kind of systems are called non-recursive systems. So FIR filters are non-recursive systems. Okay. So these are very important properties of the FIR filters. Okay. So in the next part we will be looking at the characteristics of the FIR filters and what should be the characteristics of the filter so that they are of linear phase. Okay. Characteristic of FIR filter with a linear phase. Okay. So what is the importance of linear phase? I think you all know that. So the importance of linear phase is that for any system to be distortionless, we need the phase response of the system to be linear phase. Okay. Now let us take causal FIR filter. The causal FIR filter means Hn will be 0 for n less than 0 and we are taking Hn is non-zero. Hn is non-zero for n equals to 0 to n equal to capital N minus 1 only. Okay. So Hz will be equal to summation n equals to 0 to capital N minus 1 Hn z to power minus n. So h e to power j sigma is equal to summation n equal to 0 to capital N minus 1 Hn e to power minus j sigma n. Okay. Now let us say that h e to power j sigma has a magnitude and phase okay. So this is the magnitude and this is the phase. Okay. Now as we know that group delay of a system is equal to the phase minus times the phase response of the system divided by the variable that is a discrete frequency, and the phase delay is equal to differentiation of the phase response of the system with respect to the discrete frequency. So these are the two very important formulas. Equation number 1, this is equation number 2. Now let us take the condition of linear phase, that is, let the system has linear phase with the phase response equal to minus times of alpha into the discrete frequency, that is sigma. So we can say that in this case the group delay will be equal to phase delay and it will be equal to alpha. Okay. Now as we know that h e to power j sigma is equal to summation hn e to power minus j sigma n equal to 0 to capital N minus 1. So writing this as magnitude and keeping the phase as minus alpha into sigma. So e to power minus j alpha sigma. Okay. Now e to power minus j sigma n can be written as in cos and sine. So cos of sigma n minus j sine of sigma n, and writing this e to power minus j alpha sigma into cos and sine, we will get cos of alpha sigma minus j sine of alpha sigma. So there is a space constraint here. Okay. So let me. Okay, so I'm writing it in a better format because these PDFs will be given to you as a note. So that's why I'm so cos alpha sigma minus j sine alpha sigma. Okay, now in the right hand side and left hand side, comparing the real and the imaginary part, we can get that. So we get that n equal to 0 to capital N minus 1 hn cos of sigma n is equal to cos of alpha sigma, and comparing the imaginary part we get a sine of alpha sigma, right? Now let us just say that this is equation number 3, this is equation number 4. Now taking the ratio of 3 and 4, we get that okay, divided by okay, here we'll get cos of alpha sigma divided by sine of alpha sigma. Now multiplying the equations on right hand side and left hand side, we will get that okay, by cross multiplication of the two terms we will get okay, by cross multiplying and taking the RHS to LHS, we will get this. Okay, so we have cross multiplied and taking the RHS to LHS, we will get this. Okay, now this will become a sine term. Okay, so this will become sine of alpha minus n into sigma is equal to 0. Okay, now if I write this equation and expand this equation, then we can see that this equation will be equal to h0 into sine of alpha sigma plus h1 into sine of alpha minus 1 into sigma, and so on, and we will get hn minus 2 sine of alpha minus n minus 2 divide okay, into sigma plus hn minus 1 sine of alpha minus n minus 1 sigma. Okay, so this has to be 0. Now this will be 0 only when hn is equal to h of n minus 1 minus n and alpha is equal to n minus 1 divided by 2. Okay, so these two should be the conditions for this to happen. Okay, so these two are very important conditions. Okay, now what will happen if these two conditions are satisfied? So if these two conditions are satisfied, then we can say that h0 equals to h of n minus 1, h1 is equals to h of n minus 2, and since alpha is equals to capital N minus 1 divided by 2, so I can say that this is sine of alpha n. So when we put alpha is equals to capital N minus 1 divided by 2 and write the above equation, then we will get the first term is equals to h0 sine of capital N minus 1 divided by 2 into sigma. The second term will be h1 sine of alpha minus 1, so n minus 1 divided by 2 minus 1 sigma, all the terms. The second last term will be h of capital N minus 2, so that is actually equal to h of 1, so the second last term will be h of 1 sine of alpha is capital N minus 2, so the second last term is this. Okay, so capital N minus 1 divided by 2 minus times of n minus 2 sigma. The last term is h of capital N minus 1, that is h0 sine of alpha is n minus 1 divided by 2 minus n minus 1. So if now again I try to write this equation in the simplified format is equal to 0. So I can see that the first term is sine of n minus 1 divided by 2. So I need to shift this image. Okay. So the second term will be h1 sine of, this will be n minus 3 divided by 2 sigma. The second last term will be sine of minus n plus 3 divided by 2 sigma, and the last term will be h0 sine of minus n plus 1 divided by 2. Okay, now I can see that since sine is the odd function, so I can see that this term and this term are opposite to each other. Similarly, this term and this term are opposite to each other. So the first term will this term will cancel this term, and this term will cancel this term. So the third term will cancel the third last term, and so on. And this summation will become 0. That was the requirement. So this is the condition for a linear phase FIR filter. Okay. So what is the condition? That Hn is equal to h of capital N minus 1 minus n. So this is the condition. Now there are two cases. One case n is odd, one case n is even. Okay, so in Hn equals to h capital N minus 1 minus n. So this will be Hn is, so here Hn is symmetric about n is equal to capital N minus 1 divided by 2. So this is a very important conclusion, that for symmetricity, the FIR filter impulse response should be symmetric about capital N minus 1 divided by 2. Okay, so here n is odd, so here n is equal to 9 in this case, so it will be symmetric about 4. Okay, we can see that this is symmetric about 4. Here capital N is equal to 8, that is even, so here it will be symmetric about 3.5. so we can see that. Okay, so this is important condition that you should learn. Okay, now let us take another case. Okay, So in the previous case, we have assumed that, okay, so this is 1 and this is 2. So these are the two conditions where the FIR filter can be of linear phase. Okay. Now let us take another condition. So we have taken in the previous case that the phase is equal to minus alpha sigma, where group delay and phase delay come out to be same. But if we want a linear phase, but where group delay and phase delay are different, then let us take the phase as beta minus alpha sigma. So here the group delay and phase delay will not come out to be same, and applying the same condition that summation n equal to 0 to n minus 1 hn e to power minus j sigma n is equal to mod of the magnitude and the phase, that is beta minus alpha sigma. Okay. Now applying the same method that we will be writing these two exponentials in sine and cos, the same method as we have done earlier. Okay. Mod of, so I have to shift this, otherwise there will be a space. Okay. So here it will be cos of, so here it will be cos of beta minus alpha sigma plus j sine of beta minus alpha sigma. Okay, so bracket. Now comparing the real and the imaginary part, we will get n equal to 0 to capital N minus 1 hn cos of sigma n is equal to the magnitude cos of beta minus alpha sigma. Okay, sine of, so there is a minus sign also. Okay, sine of beta minus alpha. Now this is equation number 1 and this is equation number 2 for us. Now taking the ratio of these two equations, we will get that the same method as we have done there. Okay, so there is a minus sign also. There is a minus sign also. Okay, now cross multiplying and taking the RHS to LHS, we will get okay, so there will be plus sign here. So this has to be 0. Now this summation, this will come out to be, so let me add a page here. Okay, so this summation will come out to be a sine function n equal to 0 to capital N minus 1 Hn sine of beta minus alpha sigma plus sigma n is equal to 0, n equal to 0 to capital N minus 1 Hn. So this can be written as beta minus alpha minus n into sigma is equal to 0. Now let us take a condition that beta is equal to pi by 2. So this sine function will convert into a cos function and it will become like this. Is equal to 0. So this summation can be 0 only when, so I am writing the conditions and these conditions are very important, when Hn is equal to minus times of H capital N minus 1 minus n and alpha equals to n minus 1 divided by 2. So in the previous part of this lecture we have seen two conditions where Hn was symmetric about capital N minus 1 divided by 2. Here Hn has to be antisymmetric about capital N minus 1 divided by 2. So we can prove this also. So for antisymmetric also there will be two cases, n is odd and n is even. So here n is equal to 9. So Hn will be antisymmetric about 4, that is capital N minus 1 divided by 2, that is 9 minus 1 divided by 2, that is 4, and at 4 the Hn has to be 0. So here n is equals to 8, so it will be antisymmetric about 3.5, that is 8 minus 1 divided by 2, that is 3.5. Okay, so this is the third case and this is the fourth case. So we have seen the four cases of the linear phase FIR filters. The first case was Hn is equals to Hn minus 1 minus n, that is Hn is symmetric and n was odd. Second was Hn is equal to Hn minus 1 minus n, that is Hn is symmetric with n is even. Third case is we have seen here, that is Hn is equal to Hn minus 1 minus n minus 9, that is Hn is antisymmetric, n is odd, and the fourth case Hn is equal to minus h minus, that is Hn is antisymmetric where n is even. Okay, and symmetric and antisymmetric are about this value of n, that is capital N minus 1 divided by 2. So it is symmetric and antisymmetric about this value of n. Okay, so these four are the cases. So we have seen that there are four kind of FIR filters, that Hn is symmetric where n is odd. The second is Hn symmetric where n is even. Third is Hn is antisymmetric, n is odd. And the fourth is Hn is antisymmetric, n is even. So these are the four conditions of the FIR filters. We have seen that in the previous part. Now in this part we will be looking at the frequency response of these four cases. A very simple kind of question can be asked. So how to tackle that question we will be looking in this lecture. Frequency response of the linear phase FIR filter. So let us take the case 1. Okay, so let us take case 1. Case 1 is HN is symmetric and N is odd. So the best way to solve such question is take an example. So let us take N is equal to 3, a very simple example, the simplest example that can be possible. So N is odd, so Hn will be H0, H1 and H2. Okay, only 3 values will be there, non-zero values will be there, and it will be symmetric about it will be symmetric about N equals to 3 minus 1 divided by 2, that is 1. So I can say that H0, or I can say that Hn is equal to H of 2 minus N. So H0 is equals to H2. Okay. Now if I write H e to power j sigma, then it will be equal to H0 e to power j0, H1 e to power minus j sigma, H2 e to power minus j2 sigma. Okay. Now since H0 and this term is equal, so taking e to power minus j sigma common from the whole term, we will get H0 e to power plus j sigma, H1 plus H2 e to power minus j sigma. So these two terms in H0 and H2 are equal, so they will form a cos term. So e to power minus j sigma 2 times of H0 cos sigma plus H1 is the H e to power j sigma. Now we can easily say that this is the magnitude part of the H e to power j sigma, and this is the phase part of the H e to power j sigma. So I can say that magnitude of H e to power j sigma is equal to 2H0 cos of sigma plus H1, and phase is equal to minus sigma. So this we can see clearly. Now this is the magnitude, and we can see that it is a linear phase. Okay, so there's a linear phase. Now if we look at the magnitude, then magnitude H e to power j sigma will be equal to, as we can see, plus 2 times of H0 cos of sigma. Now we can see that this function will be a even function. Okay, will be a even function, and if I plot this, then the plot will be on the sigma axis going from 0 to 2 pi. So it will be H1 plus 2H0, and at 2 pi also this will be H1 plus 2H0. At pi it will be H1 minus 2H0. So the plot will be something like this. So it will be symmetric about pi. So the magnitude plot will be symmetric about pi. So this is an important conclusion. Magnitude plot will be symmetric about magnitude. Okay. Now this conclusion is valid for all, because here I have copied from a book. here n is equal to 9, and here also it is symmetric about pi. So this is the symmetric line, and this is pi point, and this is 2 pi point. So the magnitude plot is symmetric about pi is a conclusion of this FIR filter, where Hn is symmetric and n is odd. Okay, so this finishes case 1. Now let's move on to case 2, where Hn is symmetric and n is even. Okay, so let us take a simplest example. Let n is equal to 2, and since it is symmetric, so H0, or the formula will be Hn is equal to capital N minus 1 minus n. This implies Hn is equal to H 1 minus n. This implies H0 is equal to H1. Okay, now since n is 2, so Hn has only two non-zero values, that is H0 and H1 only. Only non-zero terms. Okay, so Hz, so these are actually the examples I am taking, so that the examples are very simple and we can easily get to the conclusion without any problem. So H e to power j sigma will be equal to n equal to 0 to 1 Hn e to power minus j sigma n, that is H0 plus H1 e to power minus j sigma. Since both these terms are equal, so it will come out to be 2 times H0. Since both these terms are equal, first of all let's take common e to power minus j sigma by 2 H0 e to power plus j sigma by 2. Okay, now this will give me a cos term, so e to power minus j sigma by 2 times H0 cos of sigma by. Okay, so we can see that this is the magnitude and this will give me the phase. So the magnitude is equal to 2 times H0, where H0 is a constant, cos of sigma by 2, and phase is minus sigma by. Now if I plot the magnitude with respect to sigma, then 0, 2 pi and pi is here. So at 0 it will be 2H0, at 2 pi it will be minus 2H0, as we can see, and the plot will be at pi, the magnitude will be 0 because it will be cos of pi by 2. So the plot will be something like this. Okay, so I can say that the magnitude response is antisymmetric with respect to pi. So the magnitude response is antisymmetric with respect to pi. Okay, so this conclusion is valid for bigger values of n also, because here I have copied the magnitude plot for n equals to 8, and here also we can see that the magnitude plot is antisymmetric with respect to pi. Thus this is the conclusion for Hn where Hn is symmetric and n is even. So this is valid. So this conclusion is valid for bigger values of n also. So now let's move on to case 3. Where Hn was antisymmetric and n is even. Sorry, n is odd. So Hn is equal to minus times of h capital N minus 1 minus n. So let us take n is equal to 3. Okay. So there are only 3 terms, h0, h1 and h2. Okay. So Hn will be equal to h of 2 minus n. So h is so minus times. h0 equals to minus of h2, h1 equals to minus of h1. So from here we can see that h1 has to be 0. Okay. So Hn has only 2 terms left, that is h0, 0 and h2. Okay. And h0 equals to minus times of h2. We have seen this. Now h e to power j sigma will be equal to h0 plus h2 e to power minus j 2 sigma. Okay, because h1 is 0, right? Now since these two are opposite to each other, so I can write it as h0 minus h0 e to power minus j 2 sigma. Taking e to power minus j sigma as common, so we get h0 e to power plus j sigma minus h0 e to power minus j sigma. Okay, now we can see that this will make a sine term. So e to power minus j sigma 2j sine of sigma whole multiplied by h0. So e to power minus j sigma e to power j pi by 2 times h0 sine of sigma. So we can see that this is the magnitude part and this will give me the phase part of h e to power j sigma. So we can say that the magnitude is 2 times h0 sine of sigma and the phase is minus sigma plus pi by. Okay, now if I plot the magnitude with respect to sigma, then I am only plotting the magnitude. Okay, 0, pi and 2 pi. Okay, so if I plot the magnitude, then we can see that the magnitude will be at 0 it is 0, at 2 pi it is 0, at pi also it is 0, at pi by 2 it will be maximum because it's a simple sine curve, right? At 3 pi by 2 it will be negative maximum. So the plot will be like this. And the maximum value will be 2h0 and the minimum value will be minus 2h0. Okay, so we can say that the magnitude plot is anti-symmetric magnitude plot, and it is anti-symmetric about sigma is equals to pi. Okay, now this result is valid for bigger values of n also, because here you can see the result for n is equals to 9. Here also the magnitude plot is anti-symmetric. Okay, so we can say that when Hn is anti-symmetric and n is odd, then Magnitude plot is also antisymmetric with respect to pi. So this is the conclusion for case 3. Now let's look at case 4, the last case where Hn is antisymmetric and n is even. Okay, so let us take n is equal to 2. So Hn will be equal to minus times of h of capital N minus 1 minus n. Hn is equals to minus times of h of 1 minus n. So now since n is equals to 2, so Hn will be non-zero at h0, yeah, or will be non-zero only at two values, that is h0 and h1 will be present in Hn only. So h0 will be equals to minus times of h1 from the above property, that is Hn is antisymmetric. Now if I write h e to power j sigma, that will be equal to h0 plus h1 e to power minus j sigma. Now taking e to power minus j sigma by 2 common, I will get h0 e to power plus j sigma by 2 h1 e to power minus j, okay, sigma by 2. Now since these two terms are opposite to each other, so I can write it as h0 e to power plus j sigma by 2 minus h0 e to power minus j sigma by 2. This will make a sine term and we will get 2j into h0 sine of sigma by. So this will give me, because j can be written as e to power j pi by 2, 2 times h0 sine of sigma by. Now this is the magnitude part and this is the phase part. So I can say that magnitude e to power j sigma is equal to 2h0 sine of sigma by 2 and phase will be minus sigma by 2 plus pi by 2. Okay, now if I draw the magnitude of the function of the system 0 to 2 pi, okay, now we can see that the plot will be 0 at, so the plot will be 0 at 0, it will be 0 at 2 pi, but it will be maximum at pi, because when we put pi in this equation it will become pi by 2. So the equation will be like this, sorry, the plot will be like this, okay, and the maximum value will be 2h0. So we can say that here the magnitude plot is symmetric about pi. Magnitude plot is symmetric about pi. So this result is valid for bigger values of n also, because here I have copied for n is equal to 8 and the result is same. So we have, in this lecture we have seen for all the 4 cases of FIR filter how the filter response will be. Okay, so thank you, keep sharing these lectures, and this is the last part of the lecture series. Keep sharing these lectures and give us your feedback. Thank you.